All right, good morning, my chemistry kids. So let me go over a few things as you prepare for the test tomorrow. So let's talk about prepositions and work and all that good stuff. So when you look at this idea that work equals negative P delta V, so the whole key to this is whether work is done by a system or work is done on a system. So if work is done by a system, that means like it's expanding, it's getting bigger, you're increasing the volume. If work is done on a system, then you're smashing it together and it's becoming a smaller volume. So if you look at the equation that work equals negative P delta V, and this equation will be on the front of the test, then that's going to be a negative pressure, which is going to be in atmospheres, okay? And then you're going to have volume final minus volume initial. So let's say that your final volume is 10 liters and the initial volume was 5 liters. Okay, so this balloon, whatever it is, has gotten bigger. So that means you take 10 minus 5, that gets you a positive number multiplied by a negative pressure, that gets you negative work. So if you're increasing the volume, work is going to be negative. If you're decreasing the volume, so you're compressing something together, and then you'd have like 5 minus 10, which is going to get you a negative 5, multiplied by negative pressure, that gets you positive work. So if work is done on a system, the volume's getting smaller, work is positive. If work is done by a system, you're increasing the volume and you have negative work. Now, the other overall big equation is that your change in internal energy of the entire system is going to equal Q plus W. So Q is your energy, thermal energy flowing in or out. So that one's pretty simple. So like if you negate the work part of this, oh, I put energy into a beaker of water. Oh, that's going to increase the energy. If I take that same beaker and I put it in a freezer and I take energy out, oh, that's going to increase or that's going to decrease the energy. So that part is pretty intuitive, okay? The problem generally comes with the work part of that. Okay. So overall big ideas. So you're going to, we've talked about this a lot. You do a reaction, okay? And let's say, for example, and you measure the temperature of the water and the temperature goes down. What's going to be the sign of delta H? So one of the things you have to have completely solid is this idea that if you have a positive delta H, okay, that means it's an endothermic reaction. And if you have a negative delta H, that's going to be an exothermic reaction. That is something you have to have down, cold, don't give it a second thought. This is something that you have to know. Now, but remember, like let's say, for example, if you think back to that lab and you take a salt and you dissolve it in water and you look at that Q equals M delta T C sub P. Well, let's say, for example, the temperature goes down. So you're going to have the mass, and make sure that you include the water and the mass of the salt, okay, if that's the problem that's on the test. Make sure that you include both of those. So if the temperature goes down, let's say it drops to 15 degrees and it started at 20 and then you got the specific heat of water. So the Q, and this is what again, I cannot emphasize this enough. The Q for the water or the surroundings, in this case, is going to be a negative number. But then you switch the sign and then you make that positive when you calculate delta H. Because remember, delta H is kilojoules per mole. So if you get a negative Q, meaning that the temperature dropped for the surroundings, then delta H for the system becomes a positive value because that energy lost is equal to that energy gained. So if the temperature goes down, then you get a positive delta H. If the temperature goes up, you get a negative delta H, indicating that it's exothermic. Now, here's the other big idea that you're going to need. When you break bonds, that requires an input of energy, and when you form new bonds, that releases energy. It's exothermic. So let's say, for example, you take salt, okay? sodium chloride. Lattice structure, sodium ions, chloride ions. And you dissolve this in water. So just by virtue of the fact that if you just look at just this system by itself, and the fact that you're going to come in here and you're going to break those bonds, because you're breaking those bonds that hold those together, that's going to be endothermic. So that's going to take energy in. Now, but if you look at forming the bonds with a water molecule, okay, so that sodium ion is going to be attracted to that water molecule, to that negative end. So if that forms a bond here, then that's going to release energy because you're forming a bond. So you're going to input energy here to break the bonds, but then you're going to release energy here when you form those new bonds, okay? So just keep that in mind in terms of the big picture. The other thing that you need to have absolutely cold, no pun intended on a thermodynamics test, but here are your four combinations of delta H and delta S. So remember that delta G equals delta H minus T delta S. So make sure that you know these four combinations. Like if you go negative delta H and a positive delta S. Oh, that's always going to happen because that will always produce a negative delta G. Negative delta H, negative delta S, nature likes this, doesn't so much like this. So when you have these two combinations, that's dependent upon being below a certain temperature. If you have positive delta H and a positive delta S, that's going to require that being above a certain temperature. And if you have a positive delta H and a negative delta S, the reaction is never going to happen. Okay? So these are the things that you want to keep in mind. This is what you have to absolutely know. Make sure that you understand the ramifications of this, that delta S, the change in entropy of the surroundings is negative delta H divided by T. And again, you look at what you can measure. So if you go and you can calculate delta H because you can observe what happens with the change in temperature of the water. You can divide that by the moles. Oh, okay, right. I can calculate this based upon observable data. I divide that by the temperature, boom, there's my change in entropy of the surroundings. So keep that in mind because the delta H is for the system, okay? Also keep in mind that delta S of the universe is delta S of the system plus delta S of the surroundings. Okay? So remember, if something's going to be a spontaneous reaction, you have to have an increase in the entropy of the universe, which means your system, let's say, for example, you have a decrease in the entropy of the system, so let's say that's a negative number. So that means the increase in the entropy of the surroundings has to be a number that's positive and bigger than that one so that you end up with a delta S. Let's talk about enthalpy of formation. So let's say that you have this reaction, but we're going to make potassium fluoride, okay? So I put a 1/2 in here because that way everything balances, and I typically have this in terms of just 1 mole of potassium fluoride that I'm going to make. So remember, on this one, let's say, for example, that you're told that delta H is going to be a negative number, okay? I don't know, negative 300, whatever it is. Let's say it's negative 300 kilojoules per mole. I'm just making up this number. I don't know what it is. I just made it up. So remember, that's per 1 mole of potassium fluoride, per 1/2 mole of fluoride, or per 1 mole of potassium. Now, when you have problems like this, you have to pay attention to the question. Are you talking about, like, let's say, for example, it might say, how much energy is released in the formation of 5 grams of potassium fluoride, okay? Now, or it might say, oh, how much energy is released or absorbed if we want to make potassium. So in other words, if we want to take potassium fluoride and decompose that into potassium, versus how much energy is required to take potassium and turn that into potassium fluoride. So you have to pay attention to the reading of the question. Are you talking about the formation of potassium fluoride, or are you talking about the decomposition of potassium fluoride to make potassium. Because if you're going this direction, you're going to release energy. If you're going in the opposite direction, you're going to absorb energy. So you want to pay attention to how that is going to play out in terms of which direction this reaction is going. Okay, so on the test, I will send you, there's going to be 2 documents that I'm going to send out tomorrow. One is going to be the test itself, and the other one is going to be a chart of all the thermodynamic data that you need for the test. So it'll have like all the delta H's, delta S's, okay, that type of thing. Pay attention to the units, okay? Pay attention to the units. But other than that, you've got a whole bunch of review stuff that I'm going to send out. Study hard for the test. I will send that out. I will send that test out tomorrow morning at 9 o'clock. Don't forget, we're going to have like a study session for the AP test tomorrow night at 7 if you want to join in on that. And there we go, kids. So good luck, study hard, and we will talk to you